We've all been there, right? Sitting in a doctor's office and they shine that bright little light into our eyes. It feels like just another routine check. But in that quick flash, your doctor isn't just checking your vision. Nope, they're looking for clues to a much, much deeper story.
So what's the big secret they're trying to uncover? Well, it has nothing to do with how well you can read letters off a chart. It's all about a direct, unfiltered signal that can reveal the health of one of the most complex systems in your entire body. And there it is. Your pupils are quite literally a direct window into your central nervous system. The way they react, or importantly, the way they fail to react, can tell a neurologist way more than you'd ever imagine. And today, we're going to break down exactly how that works.
To really get this, you got to think of the connection between your eye and your brain like a high-speed superhighway. Information is constantly zipping from your eye to your brain, and commands are zipping right back in a fraction of a second. This highway has two absolutely critical lanes.
First, you've got the information on-ramp. The technical term for this is the afferent limb. So when that light hits your retina, specialized cells shoot a signal down the optic nerve all the way to a little control center deep in your midbrain called the pretectal nucleus. It's pretty much your eye reporting traffic conditions, screaming, "Hey, it's bright out here."
So once that signal gets to the brain, it's processed almost instantly, and a command gets sent right back out on the command off-ramp, or the efferent limb. This new signal travels from another nucleus, the Eating or Westphal nucleus, along the oculomotor nerve, straight back to the eye. And its message is simple. Tell the iris sphincter muscle to tighten up, right now. It's really just an elegant four-step loop. Light comes in, the on-ramp rushes that signal to the brain, the off-ramp carries the command back, and boom, the pupil constricts to protect the retina. It's simple, it's efficient, and as we're about to see, it is incredibly revealing.
But here's the thing. Reacting to light, that's only half the story. Your pupil does a very similar, yet totally distinct reflex for a completely different reason. And understanding the difference between the two, well, that's where the real diagnostic magic happens. Just look at the key difference here, the neural route. The light reflex is a simple, almost primal reflex. But the near reflex, when your pupils shrink as you focus on your phone up close, that involves higher-level brain processing. It actually completely bypasses that first midbrain station we were just talking about.
And this is so crucial. What happens when one of these reflexes works, but the other one doesn't? This is what doctors call light-near dissociation. If a patient's pupils don't react to that bright pen light, but they do shrink when they focus on something up close, it tells a doctor exactly where the problem is. There's damage in that specific part of the midbrain superhighway, but the other cortical route is still working just fine. And this all brings us to the real-world application, which is honestly like medical detective work. How do doctors use this amazing bit of biology to solve complex neurological mysteries?
Let's go right back to our superhighway analogy. What happens when there's a roadblock, or maybe a breakdown in one of the lanes? Well, the signals get messed up, and the results are these predictable, measurable signs that point directly to the location of the damage.
A classic example of this is something called a relative afferent pupillary defect, or RAPD for short. This means there's a problem on the on-ramp, that afferent limb, often because of something like optic nerve disease. The "it's bright out here" signal is either weak or just totally lost, so the command to constrict never gets sent with the right urgency.
Then you've got clues that point to a whole other kind of problem. Take Horner syndrome. This isn't about the pathway for making the pupil smaller, but about a failure in the separate system that's supposed to make the pupil bigger and control the eyelid.
And it comes with this classic telltale triad of symptoms. Number 1, a small pupil that just won't open up properly in the dark. 2, a little droop in the upper eyelid. And 3, less sweating on that same side of the face. When a neurologist sees those 3 things together, it points to a very specific kind of nerve damage.
So you can see how this becomes a kind of diagnostic cheat sheet. By just observing a specific sign, like a pupil that won't constrict well, or one that's tiny and comes with a droopy eyelid, a doctor can start to pinpoint the exact location of the roadblock on that neurological superhighway. Is it the on-ramp, the off-ramp, or a totally different set of nerves? The pupils tell the tale.
All right, so let's pull all this together. What's the final diagnosis? What does all of this actually mean for a patient?
It means absolutely everything. This is not just some neat academic exercise. Correctly reading the story that the pupils are telling could be the very first clue that there's a brain tumor pressing on a nerve or an early warning sign of a stroke. It lets doctors zero in on the damage and figure out what to do next. whether that's an urgent MRI or some other life-saving test.
In the end, it all comes down to this really powerful idea. The eye is so much more than just an organ for sight. It is a living, breathing reflection of the intricate, delicate, and unbelievably complex brain that's sitting right behind it. So the next time you find yourself in that examination chair and that light flashes in your eye, you'll know what's really going on. It's not just a checkup, it's a full-on neurological investigation, and your pupils are telling a story that just might reveal the deepest secrets of the brain behind them.